quantization error. So in this one, we're looking for an analog signal in time domain. For example, a sinusoidal signal look like this. It have a peak about 5 volts. So the peak to peak voltage value is 10 volts. So for this 10 volts, we have 16 bits to represent it. Okay, so we can actually give a very, very fine representation of each voltage level. So you can imagine that this 10 volts being divided by 2 to the order of 16. That's how many unique numbers you can have by using 16 bits. So each number can represent one voltage level, so this amount of different levels, and is equals to 153 microvolts. So this is the quantization using 16 bits. So the quantization error, the quantization error is just a half of this, which is plus minus 76 microvolts. So you can think of, for example, you have this amount of voltage, you divide it into this intervals. If you're sitting, for example, your real voltage is sitting here, it can be regarded as this voltage level, or if it's here, it can be regarded as this voltage level. The maximum error you can get is the half, right? So sitting in the middle, it may be taken as this one or the lower one. So the quantization error is actually half of the interval. So that's why it's halved. Okay, so the next part is we're gonna calculate the SQNR, which is the signal to noise ratio. So we're gonna assume the signal is a sinusoidal signal. So the signal power equals to in RMS value equals to A over root 2. So A is just the voltage magnitude. For example, it can be 5 volts in this case, and the average noise, power is Q, the quantization we just got, divided by root 12. So I will have down the derivation during the lecture, so I will not go through that. So to find out this SQNR, the signal noise ratio, we're just gonna use the power of the signal, divided by power of noise. So that's why it's called a signal noise ratio. Okay, and we also want to put it into a log mode, so you give a dB as a unit. So this SQNR equals to 20 log base 10 A over root 2. That's the signal power divided by a Q over root 12. Okay, so it's the power of signal divided by power of noise, and then we keep going. Then we can have that A is actually related to Q. So remember that how you get the Q. Q is actually, so it's just 2A that's 2a divided by 2 to the order of b, right? So in this case, a is just equals to q multiplied with 2b, right? It's q multiplied with 2 to the order of b, 2 to the order of b, and divided by a2. Okay, so we can just plug in that a into this one. So we got equals to 20 log base 10, and a becomes q multiplied with 2b divided by 2, and there is a root 2 down there as well, original root 2 there, and this one divided by this one, we can just flip it. So flip it, this root 12 up is become 2 over root 3, that's root 12 over a q. Okay, then we can cancel this one, cancel this one, so we can get, maybe a little bit, we can get this one equals to 20 log base 10 root 1.5 2 to the order of b. How many bits you have, all right? For our case, b equal to 16, then we got the result equals to 98.09 dB. So there is a general rule of that. So this S, Q, and R is approximately, okay, approximately 6 times of the bits. So you can imagine you have more bits, your S and Q is higher, the ratio is higher, right? More bits, smaller error. So the signal to error, signal to noise, small noise, error this ratio will be larger. Okay, so that's this question.